spurious, spu- spurious,
This lecture will be starting with a new section of the subject operating system. In this lecture, we will be discussing about logical versus physical address spaces. So we are going to discuss about two types of addresses, which is a logical address and the physical address. And we will also see what is logical address space and what is physical address space, how do they differ, and if they differ, how can they be related or how can we map one to another. Alright, so first of all, let us see what is a logical address. So logical address is an address generated by the CPU. So the address generated by the CPU is what we mean by logical address. And what is a physical address? An address seen by the memory unit, that is the one loaded into the memory address register of the memory. So this is what we mean by physical address. It is an address that is seen by the memory unit. And what do we mean by seen by the memory unit? That means that is the particular address that is loaded into the memory address register of the memory. So just keep in mind that logical address is the address that is generated by the CPU, and the address that is seen by the memory unit or the address present in the memory address register of the memory is known as the physical address. Now, compile time and load time address binding methods generate identical logical and physical addresses. So in the previous lecture, we have studied about address binding and we saw different kinds of address binding. We have discussed about compile time address binding, load time address binding, and execution time address binding. Now the first two, that is the compile time and the load time address binding, if we are using these methods, they generate identical logical and physical addresses. That means in compile time and load time address binding methods, the logical address, that is the address generated by the CPU, and the physical address, that is the address seen by the memory unit, they are the same. It is identical. Okay. Now, in case of execution time address binding scheme, it results in differing logical and physical addresses. But in case of the execution time address binding, the logical address and the physical address that is generated, it differs from each other. They are not the same. So in this case, we usually refer to the logical address as a virtual address. So if we are talking about execution time address binding, since the logical and the physical addresses are different, we will refer to logical address as a virtual address. So when we say virtual address, just know that we are talking about logical addresses. So now we understood what is the meaning of logical address, what is the meaning of physical address, and we saw how logical addresses and physical addresses vary in different address binding methods. Alright, now let us see what is logical address space and what is physical address space. Now logical address space, it is a set of all logical addresses generated by the program. So from the name itself, it is very easy since we already understood what are logical addresses. So logical address space is the set of the logical addresses generated by a program. So for a particular program, the starting logical address to the ending logical address for that particular program, that will be the logical address space for that particular program. And similarly, physical address space is the set of all physical addresses corresponding to these logical addresses. So the physical address space will be the set of all physical addresses that corresponds to these logical address spaces. So when we say corresponding to these logical addresses, keep in mind that if we are talking about compile time or load time address binding, the address spaces will be the same because the logical addresses and the physical addresses generated during compile time address binding and load time address binding are the same. But in case of execution time address binding, the logical address space and the physical address space will be differing. So in execution time address binding scheme, the logical and the physical address spaces, they differ. They are not the same. So if they are not the same, how will we map them to each other? How will we know that for a particular logical address space, this is the corresponding physical address space? So how are we going to map them? So this is the problem that we have and the solution that we need to find. So how can we solve it? We can solve it using this. The runtime mapping from virtual to physical addresses is done by a hardware device called the Memory Management Unit, or the MMU. So during runtime, we need to map the virtual address to the physical address. So as I already told you, when I say virtual address, remember that I'm talking about the logical address. So these virtual addresses has to be mapped to the physical addresses during runtime, and for that we are going to make use of a device called the Memory Management Unit, which is a hardware device. So let us see how does this Memory Management Unit work. So here we are going to take an example of dynamic relocation using a relocation register. Okay, so here we have the CPU, and here we have the MMU, which is a memory management unit, and here we have the memory. So the CPU generates a logical address. So let's say 238 is a logical address generated by the CPU. And this relocation register here, it will contain the starting physical address for the memory location for our particular program. So when we have discussed about the basic hardware, we have discussed about the base register and the limit register. So base register was something that stores the starting address of the address space of a particular process. So this relocation register is something similar to that. It will contain the starting physical address. Now, whenever a logic address is generated, we need to convert it to the corresponding physical address. So what we will do is, we are going to add the logical address to the address that is present in the relocation register. So here we have 15000. So the logical address is 238. So if we add them, we get 15238, which will be the corresponding physical address for this logical address. So the logical addresses, they will range from 0 up to the max value of whatever the logical address is. And the relocation register will contain the starting physical address value. And then we can get the corresponding physical address by adding the logical address to this address present in the relocation register. So for the CPU or for the user program, they think that the addresses are from 0 up to whatever is the maximum value in the logical address space. So let's say that, for example, for a particular process, the logical address space is from 0 to 300. So according to that user process, it only sees that 0 to 300. It does not have to worry about what is the corresponding physical address. Why? Because this memory management unit is going to take care of that. So the user process is only going to see from 0 to 300, and whatever it is trying to access will be added to this value here and will be converted to the corresponding physical address. So for example, if it is trying to access the first memory location, so what will be the value? It will be 0, because it starts from 0 to the maximum value, as we said in our example. So if it is 0, what will be the corresponding physical address? It will be 0 plus 15000. So it will be equal to 15000. So 15000 is the starting physical address for that particular process. So this is how we can make use of the memory management unit by this simple example of dynamic relocation using a relocation register to find the corresponding physical address for a logical address. So now we have two types of addresses: the logical address in the range of 0 to max, which I just explained now, and the physical address in the range of r plus 0 to r plus max for a base value r. So what is R? R was the value that was present in our relocation register. So in our example, it was 15000. So the physical address range is from that 15000 plus 0. And this 0 corresponds to this logical address. So R plus 0 to R plus max. So that is the physical address space that we have. So the user generates only the logical addresses and thinks that the process runs in locations 0 to max. So this is what is perceived by the user, because the user only sees the logical address space. The users think that it is only from 0 to max. But what happens inside? The memory management unit takes care of it, and it is converted to R plus 0 to R plus max. And that is the corresponding physical address. But the user does not have to worry about it. The user program supplies the logical address, and these logical addresses must be mapped to the physical address before they are used. and this is done by the memory management unit. So this is how logical addresses are converted to physical addresses. So we studied about logical addresses, physical addresses. We also studied about logical address space and physical address space, and we saw how these addresses are mapped to each other and how logical addresses are converted to physical addresses. So I hope this topic was clear to you. Thank you for watching and see you in the next one. In this lecture, we'll be discussing about dynamic loading. So let us see what is this dynamic loading and what is it used for. As we have discussed so far, the entire program and all data of a process must be in physical memory for the process to execute. So this is something that we have discussed so far in this section of memory management and under this chapter of main memory. So we have said many times that when a program has to be executed, it has to be brought into the main memory. Only then the CPU will be able to access it and execute it. And at all other times when the process is not executing, it resides in the disk or the secondary memory. Now, the size of a process is thus limited to the size of the physical memory. So the size of a process will be limited to the size of the physical memory. So for example, if we have a physical memory of 1 GB, that means if we have a RAM or a main memory of 1 GB, we will be able to execute only a process of maximum 1 GB at a time. So if our process that we are going to execute is a very large one, let's say it is of 2 GB, anyway, we are sure that we are not going to be able to accommodate that process in our main memory because it is too big. So we will not be able to load or run that process if we are trying to load it all at one time. So this is the limitation that we have. So in order to obtain a better memory space utilization, we can use dynamic loading. So in order to solve this problem, we are going to use something called dynamic loading. And we are going to use dynamic loading in order to obtain a better utilization of our memory space. Now, let us see how we can do it and how dynamic loading is going to help us to achieve this. So with dynamic loading, a routine is not loaded until it is called. So with dynamic loading, we are not going to load the complete program into the memory once it is to be executed, but we will be loading only parts of that program, which we will call routine, and they will be loaded into the memory only when it is needed. So we may have a big program. We may have a big program with multiple sections. So let's say that we have multiple sections, or let's say multiple functions. So during the course of execution, the entire functions may not be required all the time. So there may be a particular time when one portion of code or one routine is required, and there may be another time when another portion is required. So we will be loading only that portion when it has to be used or when it has to be called. So in that way, we don't have to load the entire program into the memory, but we will load only the particular parts that we need. Hence, we'll be making better utilization of our memory space. So what we'll do here, all routines are kept on disk in a relocatable load format. So all the routines will be kept in a disk. So disk means secondary memory. So they will be kept in a disk when they are not in use in a relocatable load format. And then the main program is loaded into memory and is executed. So the main program, that means the main function, will be loaded into the memory. And when we say memory, it is the main memory. So we'll be loading the main program into the memory and it is executed. And then what happens? When a routine needs to call another routine, the calling routine first checks to see whether the other routine has been loaded. So during the course of execution, let's say that we have loaded the main program into the memory and the routine from the main program needs to call another routine. Now what will happen? It will first check if the routine that it is trying to call is already present in main memory or not. And if it is already present, well and fine, it can be executed. But if it is not present, what happens? The relocatable linking loader is called to load the desired routine into memory and to update the program's address tables to reflect this change. So if the particular routine that is being called is not present in memory, then what happens? By this point, what we mean is we are trying to call that routine. So that routine will be called, and using this linking loader, it will be loaded from the disk. That means from the secondary memory into the main memory. So when we need it, we are just calling it and we are loading it into the main memory and we are using it. And at all other times, it remains in the secondary memory. And after that, the control is passed to the newly loaded routine. So that means after loading that routine, the control is given to that particular routine and it can do its execution whatever it is supposed to do. So this is how dynamic loading works. So we see that we are loading something only when we need it, and at other times it will be kept in the disk. So hence we don't need to load the entire program into the memory. So coming back, dynamic loading works. So we see that we are loading something in the routine. After that, when we need it, we are just calling it and we are loading it into the main memory and we are using it. And at all other times, it remains in the secondary memory. And after that, the control is passed to the newly loaded routine. So that means after loading that routine, the control is given to that particular routine and it can do its execution whatever it is supposed to do. So this is how dynamic loading works. So we see that we are loading something only when we need it, and at other times it will be kept in the disk. So hence we don't need to load the entire program into the memory. So coming back to the example that we took, suppose we have only 1 GB of main memory and the program is of 2 GB. So what we'll do, we are not going to load the entire 2 GB. Anyway, it is not possible. So we will load the main program provided that that is less than 1 GB, and then only those parts or routines that are currently needed will be loaded into the memory, and hence we can try to make that program work even though the main memory is less than the size of the program. So this is how dynamic loading works. Okay, so let us take a look at the advantages of this dynamic loading. So from the explanation itself, you must have already understood what are the advantages, but anyway, let's take a look. So an unused routine is never loaded. So as I just explained now, whatever is not used, it just resides in the disk and we are not loading it and we are not filling up our main memory unnecessarily. And then this method is particularly useful when large amount of code are needed to handle infrequently occurring cases. So this is also something I have already explained. If our code is very large and we need to handle infrequently occurring cases, then this method is useful because we don't need to load the entire big amount of code and we just need to use a particular portion of that code which is needed at that point of time. So although the total program size may be large, the portion that is used and hence loaded may be much smaller. So this is also something that I have just explained. Now, dynamic loading does not require special support from the operating system. It is the responsibility of the user to design their programs to take advantage of such a method. So this dynamic loading does not require special support from operating system, and it is the responsibility of the user, that means the person who is designing their program, to take advantage of this method and make sure that their program is able to function in this way. That means it should be able to load only what is needed at the particular point of time and the other portion can reside in the disk. So it is the responsibility of the programmer or the user to take advantage of this method. Alright, so those were the advantages of dynamic loading, and I hope you understood how dynamic loading works, why it is useful, and how it helps in making our computation faster and more efficient. So I hope this topic was clear to you. In this lecture, we'll be discussing about dynamic linking and shared libraries. So in order to understand dynamic linking, we need to know that when a program runs, apart from its own modules, it also needs to use certain system libraries as well. So when a program is running, we know that the program has its own modules, which is compiled and loaded. And apart from these modules that belongs to the program, it also needs to use certain system libraries which are a part of the system. So the system libraries are also required for the complete execution of a program. Alright, so keeping this in mind, we will try to understand what is dynamic linking and shared libraries. So in order to understand dynamic linking, first of all, we will try to see what is static linking, and we will see why is static linking not efficient, and hence we'll be able to understand why we need dynamic linking and how dynamic linking works. Alright, so first of all, let us see what is static linking. So in static linking, system language libraries are treated like any other object module and are combined by the loader into the binary program image. So as we just said, when a program runs, it needs to make use of the system libraries as well. So in static linking, what happens is these system libraries are treated like any other object module of the program and are combined along with the other modules of the program and are loaded into the binary program image. Okay, so to understand this, let me take a simple real-life example. So imagine that you are living in a house with your family. So you are living in your house with your family members, and think that there are different rooms in that house. So there is one room for your parents, one room for you, one room for your brother, one room for your sister. So think that there are these 4 rooms in your house. Now, let us think of some common thing that we share in a house. Like for example, a refrigerator. Yes, a fridge is something that we share commonly in a house. So we have one fridge in a house that is kept somewhere in a common place in a house, and we all share the same fridge. You keep your food there, your brother or sister may use it for keeping their food as well, and so on. So that is something that is shared. So now let's think of another way. Let's say that instead of having one common fridge, you decide to have one fridge each for all of the rooms. Then what will happen? So you will have one fridge in your room for your purpose, one fridge in your parents' room, one fridge in your brother's room, one fridge in your sister's room. Now, what happens if we do this? We are just simply wasting the space of our rooms, and we are spending unnecessary money for buying different refrigerators, which could be shared by the entire household. So static linking is something like that. Think of the fridge that we talked about as the system libraries. So here, each of the programs are going to have a copy of that system library along with their own modules. So it is just like having one fridge each for all of the rooms. So here, instead of using something that could be shared, instead of having one common thing, we are trying to have a copy of it in each and every programs. So this is what happens in static linking. And what is the disadvantage of this? You must have already guessed it. Each program on a system must include a copy of its language library, or at least the routines referenced by the program in the executable image. And what will this cause? This requirement wastes both disk space and main memory. So this is the main disadvantage. We are simply wasting the disk space and also the main memory by having a copy of the system language libraries for each of the programs. So this is what happens in static linking. So now you must be getting an idea of why we need dynamic linking. So let's see what is dynamic linking and how is it different from static linking. So in dynamic linking, It checks to see whether the needed routine is already in memory. If not, the routine is loaded into the memory. So in dynamic linking, instead of having the system libraries copies for each and every program, we are just having the system libraries reside wherever it is. And then just when the program needs to use that library, we will be loading it into the memory and we will be using it for that particular program. So first of all, it will check if that routine is already present in memory or not. If it is already there, well and good, we can just make use of it. And if it is not, then the routine will be loaded into the executable image. And what will this cause? This requirement wastes both disk space and main memory. So this is the main disadvantage. We are simply wasting the disk space and also the main memory by having a copy of the system language libraries for each of the programs. So this is what happens in static linking. So now you must be getting an idea of why we need dynamic linking. So let's see what is dynamic linking and how is it different from static linking. So in dynamic linking, it checks to see whether the needed routine is already in memory. If not, the routine is loaded into the memory. So in dynamic linking, instead of having the system libraries copies for each and every program, we are just having the system libraries reside wherever it is. And then just when the program needs to use that library, we will be loading it into the memory and we will be using it for that particular program. So first of all, it will check if that routine is already present in memory or not. If it is already there, well and good, we can just make use of it. And if it is not, then the routine will be loaded into memory. So unlike static linking, we are not going to have copies of these routines or libraries for each and every program, and we are not wasting our disk space and main memory. So this is the advantage of dynamic linking, and this is how it differs from static linking. Now the concept of dynamic linking is similar to that of dynamic loading, but here linking rather than loading is postponed until execution time. So in the previous lecture, we have discussed about dynamic loading. So that also was something similar if you can recall. So this concept of dynamic linking that we are studying now is also somehow similar to that of dynamic loading. But the difference is that here the dynamic linking rather than the loading, it is postponed until the execution time. So this is done during the execution time. So that is the difference that we see from dynamic loading. All right, so now let us discuss discuss a little more in detail about this dynamically linked libraries. So when we say dynamically linked libraries, you may be familiar with the DLL files. So DLL files are Windows way of implementing the dynamic linking. So you must have heard of DLL files, and sometimes when you may be running some programs, you may get some error saying that the DLL file is missing. So DLL is nothing but it is Windows way of implementing this dynamic linking. Okay, so talking a little more about dynamic linked libraries, with dynamic linking, a stub is included in the image for each library routine reference. So with dynamic linking, we are using something called a stub, which is included in the image for each library routine reference. Now, what is a stub? A stub is a small piece of code that indicates how to locate the appropriate memory resident library routine, or how to load the library if the routine is not already present. So as we already said, in case of dynamic linking, the system libraries or routines that a program needs to use will be located from the place where it is present, and it will be loaded if it is not present in main memory, and it will be used whenever it is needed. But the question here is, how will the program be able to locate those system libraries or the routines? How will it know where it is present, and how will it be able to load it into the memory? So in order to achieve that, we are using this stub. So the stub is nothing but a small piece of code which helps in achieving this task. It will help in locating the appropriate memory resident library routine. That means it will find out where it is present, and it will also know how to load that library into the memory if the routine is not already present. So this is the work that is done by the stub. So when a stub is executed, it checks to see whether the needed routine is already in memory. So as we already said, the stub, what it will do, it will first check if the needed routine is already present in memory. If it is already there, then well and good, it will just find the address of that in the memory, that means in the main memory, and it will just make use of it. And if not, the program loads the routine into memory. So when the stub checks for that routine, and if it finds that that routine is not already present in memory, then it will locate where is that system library or routine present in the disk, and it will load that into the memory so that the program can make use of it. So either way, the stub replaces itself with the address of the routine and executes the routine. So either way means even if the routine is already present in memory, or even if it is not present in memory, what the stub will do, for example, if the routine is already present in memory, then the stub will replace itself with the address of that routine. That means whatever is the address of that routine that we need, that address will be written into the stub. And in case, let's say that that routine was not present in memory, then what will the stub do? The stub will help in locating that in the disk. When I say disk, know that it is a secondary memory. So from the secondary memory, that routine will be loaded into the main memory, and then that address will be written into the stub. So whether the routine is already there in memory, or even if it is not there, in both cases the stub will be finding the address of that library which is either present on main memory or which will be loaded to main memory, and then that address of that library will be written into the stub. So think that when the library is loaded, the address of that library gets written into the stub. So the stub now contains the address of the routine, and then it executes the routine. So what is the advantage of this? So the next time that particular code segment is reached, the library routine is executed directly, incurring no cost for dynamic linking. So why do we say this? This is because
हेलो स्टूडेंट्स, मैं डॉक्टर गजेंद्र पुरोहित और आज मैं आपके सामने डिस्कस करने वाला हूं न्यूमेरिकल इंटीग्रेशन। बहुत ही इंपॉर्टेंट टॉपिक है और इस टॉपिक पे गेट में और कॉम्पिटिटिव एग्जाम्स में भी बहुत क्वेश्चंस पूछे जाते हैं।
Hello students, my name is Dr. Gajendra Purohit. You are watching our YouTube channel where I upload videos for engineering, maths, BSc. If you are preparing for competitive exam where higher mathematics is asked, our YouTube channel is very helpful. Today we will study numerical differentiation. Numerical differentiation is connected to the concept of interpolation. If any data like x and fx is given and it's at equal intervals where you have to find the value of dy by dx at any particular point, whatever we used to apply like Newton forward and backward on the Stirling, just apply same concept here and you have to use the concept of derivation, right? We will derive the formula and I will explain the concept to you because generally students just memorize the formula. You don't need to memorize the formula. If you remember the formula, then you can easily derive it and calculate the value. So today I will explain you that how we can find the value of a derivative using Newton's forward and backward method. All right. After this, we will talk about Stirling in the next video. And then when we have unequal intervals, so how do we find its derivative? That you will see in our upcoming videos. Let's begin, students. Backward, which was for lower value. Whereas to find the middle value, we had Stirling. Whereas we will discuss numerical differentiation for equal intervals. Here we have three formulas, right? So Newton forward was for upper value and the other was Newton backward, which was for lower value. Whereas to find the middle value, we had Stirling formula, right? If you don't know this, then you can click on I tab and watch the videos where I have explained it. Normally what happens is, like I will give you an example. Let's say that we have x given and we have fx here. I will try to explain it to you. So as you can see, we have a value 1981, which includes the population of a specific place and the population number is 100. And in 1991, the population is 150, while in 2001, the population is 170, right? And the population in 2011 has reached 300, whereas in 2021, it reached 450. I hope you can see this clearly. So you have this data right here with you and you have to find. This means that here we have x and we can call this y, right? So the question is that we have to find the f of 1982. We know how to get the Newton forward, but if you are asked to find f dash 1982, you might also get a question where you have to find dy by dx at x is equal to 1982. So how do you calculate this? You need to understand this. If you need to find the second order derivative, then we will use the Newton forward formula here, but we just have to differentiate this formula. How are we going to do it? Look at the screen as this is important. We will do this formula with respect to u. This will come to our side y dash a plus hu, and since we are doing with respect to u, so this h will come in front. We are doing this with respect to u. We will have 0, and when we will do it with respect to u, this will be del y. We also call it fy. We will differentiate this u square minus 1 and this will become 2u minus 1 upon 2 factorial, which will be del square y plus we will multiply this. So we will get u square minus 3u plus 2, and this u here, if you multiply this, then it's u cube minus 3u square plus 2u. Now let's differentiate it. So this will come 3u square minus 6u plus 2 upon 3 factorial. This will be del cube y, but we can also use fx in place of y. So if you want, then you can use f also here. Okay, clear? Then f dash a plus hu, and this h will move below. So it will be del f, right? Because we have kept y as f. We have put fa here, okay? Plus this will come to u minus 1 upon 2 factorial, which is 2. That will be del square fa plus 3u square minus 6u plus 2 upon 6. So this will be del cube fa. In this way, this formula will keep going on. We have found the formula, and with the help of this formula, what we are going to do, we will calculate the value of this derivative. How